Today, we're diving into the secrets of a truly ancient object in our galaxy, the globular cluster Messier 3. We're going to see how astronomers are using two totally different methods, one like a wide city census, and the other like a deep dive detective story, to piece together its incredible history.
Okay, so I want you to picture this. Deep in the night sky, about 33,900 light years away, in a little constellation called Canes Venatici, there's this glittering city. It's not made of steel or glass, but of starlight, gravity, and just immense amounts of time.
And when I say city, I mean it. This place is home to almost 500,000 stars, all packed together in this huge, glittering ball. They've been bound together by gravity, swirling around each other for over 11 billion years. That is unbelievably old, almost as old as the universe itself. So that's the thing, right? When you have that many stars, all tangled up in this ancient dance, how on earth do you begin to figure out what's going on in there? How do you read the stories that are hidden in all that light? Well, that's the exact challenge that astronomers face with Messier 3, or M3 for short. And the way they do it is pretty cool. They treat it just like a massive, mysterious city that's waiting to be explored. So what exactly is a globular cluster? You can really think of it as a dense cosmic metropolis. You know how our galaxy has these long, sprawling spiral arms? This is the opposite. This is the tightly packed, ancient downtown core, where stars are just crammed together by their own gravity. And M3 is a real A-lister among these star cities. It's one of the most studied ones out there, mainly because it's famous for having more of these things called RR Lyrae stars than any other cluster we know of. These are old stars that pulse, getting brighter and dimmer with a really predictable rhythm. They're like cosmic lighthouses, which makes M3 just a perfect lab for testing our big ideas about how stars live and die. So let's say you want to understand the city. What's the first thing you do? You take a census, right? You get a big picture view of who lives there, and that's exactly what our first team of astronomers decided to do. Now, trying to find the few stars that are changing in a field of 500,000 is, well, it's a nightmare. So they use this brilliant, almost simple technique called image subtraction. You take one perfect picture, and then you come back later and take another one. Then you use a computer to digitally subtract the first image from the second. All the stars that stayed the same just disappear, and you're left with only the ones that flickered or flared up. It's genius! And you know what? It worked like a charm. This survey found 180 of these variable stars. And get this, a whopping 12 of them were brand new discoveries, stars that no one had ever cataloged as changing before. So what this kind of survey gives us is the grand tour. It's like creating a demographic map of our star city, showing us where the different populations of stars are and just generally what they're up to. But what if you don't care about the general population? What if you're a detective hunting for the city's most unusual, most hidden residents? For that, you need a completely different strategy. It's time for a cosmic detective story. The targets of this hunt are something called millisecond pulsars. And these things are just wild. They're basically zombie stars, the dead cores of massive stars that get spun back to life, whipping around hundreds of times a second because a nearby companion star is dumping material onto them. They're like perfect cosmic clocks, but the real mystery is finding that companion that did the spinning. To crack a case like this, you need a two-pronged attack. First, you use a giant radio telescope, in this case the FAST telescope, to listen for that faint, super-fast radio pulse to nail down the pulsar's location. Then you point the Hubble Space Telescope at that exact spot to look for the tiny faint glow of the companion star itself. So, the mission was set. A different team of astronomers had solid radio coordinates for 5 of these millisecond pulsars inside M3. The big question was, could they use Hubble to finally identify their mysterious partners? And the results were this fantastic mix of home runs and a really intriguing plot twist. So let's open up the case files. First up, we've got case file M3B. The radio signal basically gave them an X marks the spot. They pointed Hubble right at it, and boom! Sitting right there in the search area was a faint blue star. They had their suspect. But here's the smoking gun. When they plotted that star's color versus its brightness, it landed exactly where their models say a helium white dwarf should be. This is the signature of a star that's had its outer layers stripped away by a companion. It was a perfect match. Case closed. And the detectives were on a roll. They used the same method to go after two more pulsars, M3D and M3F, and they nailed them too. As you can tell from these images, these guys were even fainter, really pushing what Hubble is capable of. But the evidence was solid. Two more cases solved. But then we get to case file M3E. This one was a real head-scratcher. There was a star right there, right where it should be. But look at these two images, taken 15 years apart. See that star? It's moved. That's really not something you'd expect for a star that's actually part of the cluster. And here is the clue that cracks the whole case wide open. This plot shows how all the stars in the cluster are moving together. See that big clump in the middle? That's M3. And our suspect? It's that red dot, way off on its own, moving in a completely different direction. It wasn't the companion at all. It was just a random star in the foreground that happened to photobomb the crime scene. The real companion is still out there, hiding.
Okay, so let's zoom back out. We've got one survey that's counting the population and another that's tracking down these super specific individuals. What do we actually learn when we put these two stories together?
Well, it brings us right back to our city analogy. The wide survey is the mapmaker, charting the city's neighborhoods. The deep hunt is the biographer, writing the amazing life stories of the city's most unusual residents. You absolutely need both to get the full picture. And that's really what makes modern astronomy so powerful. You combine different tools, like radio and optical telescopes, and you start to uncover secrets that neither one could find on its own. We're testing our biggest theories about stars in these wild, crowded environments. We've now got 3 confirmed pulsar companions. And even for the ones we didn't find, we now know how faint they have to be. So even when you fail, you're still gathering crucial data.
And just think about it. All of this, from just one star cluster out of hundreds in our galaxy, it really makes you wonder, doesn't it? If one single ancient city of stars has this many puzzles and mysteries hiding inside, what other incredible stories are out there just waiting for us to figure out how to read them?